signaling there's somebody still coming. I don't know. Okay, well, we'll go ahead and start. Connell can come in when he wants. There he is. Anyway, welcome to the new academic year's DTM seminar series, the first one for the year. Today's speaker is Evan Groopman from the Naval Research Laboratory in DC. Evan, I've known Evan a long time. He got his undergrad degree at Washington University in physics, and then his PhD in physics at Washington University in the same research group where I had done my degree 20 years earlier. And as part of his PhD, we did some collaborative projects, so that's great. He finished his PhD in 2015, working on pre-solar grains by various techniques of TEM and nano-SIMS and synchrotron X-ray microscopy. And after that, he went to NRL as a postdoc to work on a new instrument that was being developed there that is now called the NAUTILUS, and he'll tell us all about it, an exciting new type of SIMS accelerator mass spectrometer. And he's starting to apply it to all kinds of interesting projects. After, 2 years as a postdoc, you became a staff member? Roughly. Anyway, he's now a permanent staff member on the scientific staff at NRL. And he agreed to come tell us about his exciting new lab and some cool results he's got. So thanks.
Okay. Anyone hear me? Thank you, Larry. And so Larry did mention that he was on my dissertation committee, so it's somewhat his fault that I escaped from graduate school. Okay, so thank you, Helene. I don't know if I see you, and Susanna, and everyone else who made it possible for me to come, and of course for attending this talk. First I want to say how truly sorry I am for all of you. I wasn't much more than an acquaintance to Eric, and I was certainly looking forward to speaking with him. But I know, I've had several colleagues and friends pass away as well, and so, my condolences. I'm sorry. Despite the circumstances, it's pretty good to be back. I was very happy to be invited back to Carnegie. I visited over the years in collaboration with Larry and others. So this is back in 2012. There I am at the Mud Cup, helping DTM defeat their arch rivals from across the laboratory. I'm sure no one was keeping score, but I didn't keep score. But anyway, so the collaborations and visits here have been very fruitful. A significant number of my publications have been with data collected here at TTM or in collaboration. And we were looking for a picture from the pre-solar grain workshop back in 2014, but couldn't find it, but it would be right here. So what do you need to make new discoveries? I think I've put it in kind of a three-legged stool. You may disagree with some of this, but I think you need the right personnel, the right equipment, and the right samples. And these all feed back into each other, back and forth. Okay? So you have to identify what the interesting problems are, use, maintain, and develop new instrumentation to apply to those problems, and of course apply the appropriate instrumentation to the samples that you have. And I think a really good example of this is a recent paper by Nan Liu, who was a postdoc here, and other collaborators and her co-authors here and at the Naval Research Lab, looking at problems in a different way, applying techniques such as Raman and EDX to the problem of identifying pre-solar silicon carbide X-grain populations in a non-destructive fashion. Okay, so this was something pretty novel, and it can change the way how we identify these grains and push cosmochemistry forward. What I'm going to start the talk with is my experience in the last 3 years, really pushing the technique, secondary ion mass spectrometry at the Naval Research Lab, and pushing the limits of this technique so that we can apply it to new and interesting problems and samples. So what is SIMS? Many of you here are probably familiar with it. When I refer to SIMS throughout the talk, I'll just be talking about dynamic SIMS, in case there's any tough SIMS people out there. But basically, you choose SIMS because you have a high sensitivity to most elements in the periodic table. It is the most sensitive surface technique, and you can go down to ppb sensitivity for certain elements. And in the range from hydrogen to uranium. And you also have high lateral and depth resolution. This allows you to do imaging, look at heterogeneous materials on a spatial scale, and differentiate different materials. And the basic premise is that you generate a primary beam of ions that you shoot at your sample. You sputter away atoms of the sample, some of which are ionized, and then you pass these through a filter, a mass filter, so you can separate them and pick individual isotopes to measure. And this is analogous to how a prism refracts the different wavelengths of light and allows you to isolate those. And given that it's one of the really important aspects of this, as I mentioned, was the imaging and the ability to look at heterogeneous material on a spatial scale. So this is a little video. There's a silicon wafer, and so this is a mass-filtered image on silicon-28. So everything you see in the bright region is silicon-28, and then there's a pattern of tantalum on top, so there's no signal there. So this is an image. You can see the silicon, but when you move over to another region of the sample, you can see that there's a silicon-rich PMMA film on top, and eventually when you sputter away through that, you see the negative tantalum pattern here and the silicon coming through. And this just demonstrates how much of a surface-sensitive technique this is, because this is a film that was just from the plastic box that this wafer resided in between being used in the instrument. And the film migrated on top. And so this is really only a nanometer or so thick, and we can see it visually, which is quite striking. Okay. So what are the SIMS paradigms? Most of you will be familiar with the 3F, 1270, and shrimp kind of SIMS instruments that are often used, and also the nanosims. And most of these instruments are similar in how they produce the ions that they measure, usually with an oxygen or cesium primary beam. You chemically enhance the matrix to increase your ion yields. And then you mass filter, as we were mentioning, the molecules. And really, these types of instruments differ just in their geometry and how they extract the ions, the kind of spatial resolutions that they can achieve, or whether they use multi-collection or not. So the big problems for SIMS are, what do you do with isobars and molecules that interfere at those masses of interest? And generally with all these techniques, you either increase your mass resolving power, so you can separate nuclear masses that are closer and closer together, or you use some combination of energy filtering to suppress the molecules. And the key to doing any kind of analysis is really you want to maximize your signal-to-noise ratio for your application. So one example, for the nanosims is that with its higher spatial resolution, you can reduce the noise from the outside, from regions that are outside of your region of interest. Okay, so that's just one way to suppress the background of the noise. Other ways, of course, try to increase the ion yield of your sample to increase the signal. Okay, so what we've developed is a combination SIMS, it's a CAMECA 4F, with a single-stage accelerator mass spectrometer detector. Okay, so this is a standalone SIMS instrument that has an electron multiplier and Faraday cup detectors, but alternatively, you can deflect the ion beam that you've mass filtered into this accelerator. Okay, so you accelerate the ions by about 300 kilovolts and pass them through a gas stripping cell, which dissociates all of the molecules, and then you can mass and energy filter afterwards, okay, and detect the ions. And so what this really allows you to do is suppress this noise. You can put it down to the floor, almost to zero, that molecular background electronic noise. Okay? So the front end is just a SIMS. We can open it up using low mass resolving power to get higher transmission, open our energy window, but really, extracting the ions from the sample is the same as SIMS. Okay? We just remove the noise on the back end. Okay? So getting a little more abstract, as I've been leading towards, any kind of mass spectrometry is just an ion source, a detector, and a series of filters that you put in between. So the nanosims and 6F, they have the ion sources and detectors, and they use an energy filter and a mass filter to remove unwanted signal. The NAUTILUS is a little more complicated, but not that much more. Basically, you have your SIMS instrument right here, but alternatively, we can send the ion beam into that gas stripper cell, and then we mass and energy filter a few more times before going to the detector. But having this mass spectrometer combination allows you to do fun things and do certain measurements in a different way than ordinary SIMS would by itself. And I'll elaborate on that a little bit. First, though, this molecular dissociation is an incredibly efficient process. So this is basically a plot of how much argon gas we flow into our stripping cell, which is completely controllable before the measurement, versus the intensity of the ion counts we measure at the end of the accelerator. So this is the atomic ion transmission with increasing gas flow. And basically, after this quick drop-off, which is some charge state change that goes on, basically this exponential decay is just scattering loss. Okay? The more gas you have, the more scattering, the more attenuated your signal is. But the molecular ion signal that we measure drops off many, many orders of magnitude more quickly. So normally when we operate this in just a filtering mode, by getting rid of the molecules, we operate at around this amount of gas flow. And of course, you can modulate it based on your matrix. If you have less molecular background, you can run with slightly less transmission loss. But basically, you have a trade-off of about 60% loss in transmission, depending on your element, for 4 to 5 orders of magnitude reduction in your background. And that's usually enough to completely clean up your signal. But it also means that you can look for peaks that were trace element peaks that were otherwise swamped by this background from a normal, there's the normal matrix background. And then a couple of plots of the charge state distribution, because when you have energetic ions in collisions, you lose some electrons. You get a few more multiply charged states, but charge state 1 is the predominant charge state. So we have 2 different modes of operating this instrument. One is in the filtering mode that I mentioned, and basically, when you generate your ion source and send it into the SIMS, you have all different masses coming off of the sample. You mass filter to select a particular mass of interest. And then we send this signal, which is full of molecules and atomic ions, into the molecule filter, break them up, and then further select just that mass of interest again. An alternative methodology is to look at fragments. So for various reasons, you might want to send in a molecule signal from the SIMS, potentially because it has a higher ion yield. And you send all that in, mass filter to, say, an oxide of a molecule or an oxide of an element, and then break it up and measure that element afterwards. And this allows you to do some very fun things. So for instance, with uranium oxide, this is a plot of uranium fragments from different oxide molecules we sent in, UO and UO2, versus the oxide ion transmission through the SIMS. And normally, we run right about here, where you get that 4 to 5 orders of magnitude reduction in the molecule signal for a trade-off of 60% reduction in the transmission. But right now, we're not trying to remove that background signal because no other element, no other isotope, except that one mass is going to make it through that second mass spectrometer portion. So really, we can operate up here, and we can remove, say, only 90 or 99% of the molecule signal, converting that into the signal that we're going to measure. And so you have less reduction in transmission up here. So you can really play around with how you want to tailor your analysis depending on the kind of matrix that you have. And you have a lot of freedom here. So these are some pictures of the NAUTILUS lab at NRL. We have our 4F here. It's on this green stand. And right here, and it leads into the accelerator mass spectrometer that's behind in this cage for electrical safety reasons. And we've built all of the control software and hardware ourselves, trying to use as many off-the-shelf parts as we can. We have our little control station right here. Okay. So some of you might be familiar with previous incarnations of this work at the lab and other things that were involving pretzel magnets and radiocarbon and cold fusion, but these things didn't work for many reasons, and this should not be what you are thinking of today. Okay? We now have a new laboratory that works. We can make real measurements, and I hope to show you that we have an effective instrument that we can apply to a lot of different techniques. So what are those difficult SIMS problems? We've been mentioning that molecular isobars are hard. Hydride molecules, especially at high mass, oxide molecules, especially over the rare earth element region. You have complex samples with unpredictable backgrounds. And if you want to make any sort of molecule correction, which is the standard thing you do in SIMS, you can't have non-perturbed isotope ratios. You have to assume they're terrestrial. There's some other problems as well, but I'm not going to talk about them here because we only have an hour or less. So what do those hydride molecular interferences look like? This is a simulation that my colleague David ran, looking at the transmission of different peaks. There's PbO2 and uranium hydride, and we're trying to isolate this peak of uranium-236, which is not present in nature. It's only present at very low amounts, and it's a signature of re-enriching nuclear fuel. So, at low mass resolving power, all of these peaks overlap. You increase it and you can separate out the dioxide, but then you have to go to increasingly higher mass resolving power, and your transmission falls to almost nothing in order to separate these peaks at only the 10% peak height. Okay. Rare earth elements, these are also quite tricky because they create copious molecular oxides and other complex molecules that can swamp out your signal, especially when you're looking at trace elements. So what people normally do is they try to put a small energy offset of a few tens of eV on the sample, and you take advantage of the fact that the energy distributions of atomic ions and molecular ions are different. And by applying this energy offset, you can suppress your molecular ions more quickly. And if you use an energy window that you set out here, you can measure a mostly atomic ion signal. Now, a couple of issues with this. I mean, in general, it works very well. But a couple of issues is that you reduce your transmission by several orders of magnitude when you do this. And every atomic ion and molecular ion, so every element, has a different energy distribution. And so you have to calibrate all of these and calibrate them relative to each other in the sample and in the standard. And this is pretty time-consuming. And then you have to measure some 47 masses for all of these oxides and atomic ions so that you can put this into a deconvolution algorithm and pop out your answer. Now, this doesn't work very well when you have trace elements, because when you subtract a big number from a big number, you have big errors. You can't find that small signal. And it also requires knowing the isotopic composition ahead of time. And this doesn't work in perturbed isotopic systems such as nuclear fuel or in pre-solar grains. So what we can do, and this is a mass spectrum, secondary mass spectrum in the rare earth element region from a hibonite grain, and compares the SIMS alone in blue versus the SIMS-SAMS or NAUTILUS combination in red. And so the real signal is the one in red, and this particular hibonite has very, very few heavy rare earth elements. And the molecular signal that's on top of it, just from these oxide ions, is 3 to 4 orders of magnitude larger than the underlying signal. And it sounds a bit like an infomercial, but all we have to do is turn on the gas. It's that easy. And we can get rid of this signal. We don't have to go through this labor-intensive deconvolution technique that doesn't work very well with this particular sample. Okay. So we're using a single-stage accelerator mass spectrometer, which is a bit different than your traditional tandem AMS. And the big difference is that tandem AMS can only introduce negative ions into the accelerator. This is because you have negative ions that go in, they're accelerated towards a big positive potential, they go through the gas stripper. Because they have lots of energy, they lose electrons, go through a charge state change, and come out positive ions. Then they're accelerated away from that. You can't do this with positive ions because at high energies, or sufficient energy, you can't gain more electrons when you're undergoing collisions. You can only lose them, essentially. Okay. So what does this mean? Well, most of the elements in the periodic table are electropositive. So everything that's here in green and yellow and orange, these preferentially produce positive ions during the sputtering process. So with our single-stage accelerator being able to inject positive ions directly, that means we can gain orders of magnitude increases in sensitivity, and we can push the size of our analysis region smaller and smaller. So one of the projects we've been working on is we want to test the limits of sensitivity. And with some collaborators at Lawrence Livermore, use this for establishing whether it's useful in a nuclear forensics standpoint. Okay. So for nuclear forensics or actinide forensics, usually you're interested in any of these isotopes that are in the green or the blue, but we can concentrate just on some of the uranium isotopes with their abundances over here. So 3 of them occur in nature in these amounts, and the other 236 is essentially not there in nature, but is a signature of re-enriching nuclear fuel, because you make uranium-236 by capturing neutrons on 235 the ones that capture and don't cause a fission event. So normally with SIMS, because you can't do this separation with high mass resolving power, you measure the 238 hydride over here, and then you infer that it's the same relative intensity on this one, and you can do a deconvolution. And again, this works reasonably well in some systems. However, the molecular corrections are substrate dependent. In a big heterogeneous sample, they wouldn't work very well, and they can only go so far. And one of the big issues is that if you have a mixed oxide fuel, if you have any amount of plutonium-239 in here, that's going to be in that 239 mass signal as well, and so this deconvolution doesn't work. So what do? You just get rid of the molecules and measure them directly. So our collaborators made a series of different glasses for testing. And these glasses, the three of them have a nominal composition of about 300 parts per million of uranium, and another one all had different abundances of uranium ranging from about 4 ppm to 400 ppm, but with different, and with the same uranium isotopic composition, about a 50-50 mix. Okay, so we can test detection limits in both settings. Okay, so these are some of the data, our preliminary data from measuring these glasses. And for most of these, so the dashed lines are the certificate values for these glasses. They were measured at Livermore. And for most of them, we see that we have a pretty good, we're spot on with the certificate values, just measuring a few spots. I'll come back to this blue one, which is significantly lower than the certificate value in both the 234 and 236, although it has a very tight bunching. So these analyses seem to be precise, but not very accurate. Okay. And in this particular sample, we measured with a 10 nanoamp probe over here, but because it's fairly low in abundance, only 4 ppm of uranium, we increase it to 100 nanoamps to see if we can get a slightly more precise measurement. And we could. So the other three glasses, these are all the ones that have different, these are all the ones that have the same abundance of uranium, but different isotopic compositions. And for all of them, in the 234 versus 235, we were spot on with the 235, but the 234 ratios were substantially lower than the certificate values. Interestingly, they all seem to fall along a line, so some mixing line. So we were suspicious that perhaps there was a spreadsheet error or something else with these data. And over here on the 236, it seems like a very similar situation. One of the glasses is supposed to be natural uranium composition, so there should be no uranium-236 in it. But we measured a little bit, a non-zero amount of 236 in this A glass. So again, we're a little suspicious. So we decided to measure a number of other natural uranium minerals in addition to this A glass to see if we had the same signal. Is this really an instrumental artifact, or is it something with the sample? So these are just some example depth profiles from the A glass with a 10 nanoamp probe, and then also from monazite and titanite minerals that have some uranium in them. So here, the orange spots are the uranium-238 hydride signal that we measured. So this can be thought of as the background signal for any of these measurements. Okay? And as we go through the 10 nanoamps on glass A, we see that there is a significant signal that occurs, very low count rate, but it's a lot different than the background, and it's fairly periodic. So we were further suspicious, increased the ion beam current, and we see there is definitely a signal there. This is real uranium-236 in this sample. It's not quite natural. When we measure the monazite, absolutely no counts. Titanite, you see this count right here and a little burp right here, and we later were able to trace that down to some electrical work that was being done on the building over. But even if you get sporadic counts over here, our background is essentially zero. Okay? You have these individual counts that are clearly not part of the signal. So it turns out that this measurement of uranium-236 is a 260 part per trillion measurement of 236 in the sample. And we were able to see it with just a 10 nanoamp beam. You can't make a very good measurement of it, but you can see that it's there. And this is because the background is so low. With quiet electronics and removing the molecular background of the signal, you can really make a direct measurement. So we informed our collaborators that we saw this, and they said, oh yeah, well, we're Livermore, so we do have some contamination with 236 in some of our samples, but we didn't think you could see it. So that was kind of fun. So we still have, so these are all the measurements that we made across the certificate ratio. And we see that for most of these samples, it's very linear with no deviation. So this gave us some confidence. These guys are still a bit low, which is a bit strange. And this is to clean that up a little bit, these are the average ratios from all of the measurements of each sample. So what is going on with these guys? Everything else is nice and linear over almost 6 orders of magnitude of certificate ratio. Okay. So recently, just last month, we got some validation, which is great. So our colleagues remeasured these glasses with ICP-MS and discovered that, yes, the signals agree within errors. We were kind of spot on, which is great. It turns out that the person who ran the instrument last time, who no longer works there, had made a mistake in the measurement. So that was it. Nice validation. And it turns out that in further inspection, the scatter that you see here is real scatter within the samples. These samples aren't homogeneous, unfortunately, down to the micron scale. But they're still probably good enough for a lot of nuclear forensic work. Nuclear forensics involves lots of heterogeneous materials as well. So we're getting some of the way there, and we've been able to test our sensitivity along the way. But really, I think this highlights the importance of being able to make direct, uncorrected measurements. Because if you were trying to do these hydride corrections for these measurements, and the sample is heterogeneous spot to spot, your correction, if you use the same correction every time, you're going to miss the mark. Okay? It's not going to be accurate. Okay. So we further decided to test this, looking at some particles, because lots of safeguard work is very interested in particles. So we made a dirty mount of CRM U500 particles. So these have an equal proportion of uranium-235 and 238 in them, with a bunch of crushed monazite dirt in the background, so something with a natural uranium composition. So these kinds of samples, it's very easy to tell based on the major uranium isotopes which is which, and you can see that here, comparing the SIMS and the SAMS. Yeah, we can see those particles on the SIMS already. It's great. But when you look at the uranium-236, I know this is a little hard to see, but we didn't want to smooth the data. These are the raw data, so the real pixels that we measure. Okay. You'd see a clump here on the SIMS and here, 2 particles. Okay, that matches the majors. But on the SAMS, because we've eliminated the background out here, there's this other really tiny particle down in there. It's very difficult to see. So we zoomed in and took a few other images over these particles. And so this is basically the first few cycles of the images that we took and the last few cycles over an imaging acquisition. And we consumed this small particle during that time. But it was definitely there, and you can see it. On the SIMS, though, it's completely within the background. And when you take a little box over here, this region of interest, you can see that, yeah, on the SAMS, this particle was there, but it's completely swamped on the SIMS side. And it's swamped even though you can tell that the major isotopes are U500 on the SIMS alone. You don't have to use the SAMS for that in this case. So that was pretty fun. So I jumped ahead to this molecule-free ion imaging. So I want to take a step back and talk about how we do it. And one of the fun things is that because this is a standalone SIMS instrument up front, imaging, reconstructed raster ion imaging, works the same way on our instrument as it does on any other SIMS. And this is because for imaging on an electron multiplier and a Faraday cup, over here, as long as we're sending the ion beam from every pixel into the accelerator at the same place, which is what you do to get an image right here, you can reconstruct the image in the same way. All you have to do is send your additional timing signal from the ground over fiber optic to the 300 kilovolt accelerator up here, and you can reconstruct an image. So this works by rastering your primary beam across the sample and keeping track of the pixel location. You use some deflectors to correct for the trajectories of the ions when you're off the center of the axis. Break apart the molecules so you get only an atomic ion signal, and then you can reconstruct your image. And what's a lot of fun as well is that we can interleave these kinds of measurements, and those were the previous images you saw before. We can measure on the SIMS, then on the SAMS, SIMS, SAMS for different isotopes. So we can actually get a nice comparison of what that molecular destruction is buying us. Okay. So the application now, the main part of the talk is about the Oklo natural nuclear reactor. Okay, so this is a system with perturbed isotopics where you can't do these kinds of corrections that we've mentioned before on the SIMS for all systems. So for those of you who aren't familiar with the Oklo natural nuclear reactors, this is an incredible system, an incredible event. So in Gabon in Central Africa, about 2 billion years ago, you actually had sustained nuclear reactors and reactions taking place over the course of tens of thousands and up to 1 million years in some instances. So what are the conditions that you need to have a natural nuclear reactor? Because it can occur today. So you need uranium, the main fissile isotope, 235, to be enriched over its present-day abundance of 0.72%. And most anthropogenic light water reactors have an enrichment of 3 to 5%, 235. And so about 2 billion years ago, you had this condition that because uranium-235 decays 6 times faster than 238, the abundance was naturally higher, and it was about 3%. So we're part of the way there. You have to have a high concentration of uraninite. UO2 is the fuel used in anthropogenic reactors as well. You have to have a neutron moderator, either water or carbon, and that's because uranium-235 has a higher probability of fissioning for thermalized low-energy neutrons. Fission releases high-energy neutrons. They have to collide with something in order to be reduced in energy. And you also need minimal neutron poison, something like boron or vanadium or some of the rare earth elements that capture the neutrons and then don't release their own neutrons to keep the cycle going. So one of the fun aspects is that these high concentrations of UO2 existed because the atmosphere at the time and the water were highly oxygenated, this great rusting event because of cyanobacteria photosynthesizing for the first time. And so you can't form these kinds of deposits without that oxygenation. So in a kitschy sort of way, life is responsible for all of the nuclear reactors, both past and present. But the discovery of these reactors is really a triumph of mass spectrometry. So you had Francis Perrin in France, a nuclear physicist, looking at a bunch of uranium ore samples from the region, and he measured that the abundance of uranium-235 was 0.717 in one ore sample that he had. And of course, this is greater than the variation in the entire solar system that occurs naturally. So he knew that something had to be strange. Okay? And they went back, found other samples, and later discovered that yes, there really were natural nuclear reactors operating underground. So we have a sample from reactor zone 13, which is a very well-preserved reactor zone. It has this dolerite dike, so some local volcanism that happened about 1 billion years afterwards. And in the Oklo region, there's 16 reactors, and then there's one also isolated down here. Okay? So the water, the groundwater, not only acted as a neutron moderator, slowing down those reactions, but it also prevented this runaway thermal expansion and kind of chemical explosion of the reactor and allowed them to cycle on and off periodically. So what happened is the water moderated the neutrons, allowed fission to occur, and then when it heated up, the water converted to steam and left the area, and then there was no longer a moderator. Okay? So you only had fast neutrons, and the criticality ceased. When it cooled down again, water flowed back in, and the moderated reactions resumed. And so this was work that was done by my co-authors and colleagues a few years ago by looking at xenon isotopes. And they were able to determine that the reactors cycled on for 30 minutes and off for 2.5 hours over tens of thousands of years, which is pretty incredible. Okay. So from this sample, reactor zone 13 was found to be the most active of all of the reactor zones, but also the shortest lived. So 24,000 years versus several 100,000 years. Okay? And from this sample, we were able to make a measurement of, we believe to be the lowest ever natural uranium isotope ratio. So it was 0.36% or so from these samples. So that tells us that our particular sample is from as close to the center of the core of this reactor as possible. And this is the uranium-235 to 8 ratio across the core of this reactor. Okay, so this is what our sample looked like. It's about 3 by 4 millimeters. Most of what you see in here is uraninite grains that are highly contrasting, and then the veins in between are this rare earth aluminous phosphate that's a secondary mineral. And there's some other secondary minerals as well. These pits that you see are laser ablation pits, and this was from Alex Meshik and his co-authors' work on the xenon on this sample. Okay. If we zoom in, it's a secondary electron image, again, the aluminous phosphate and the uraninite grain, and some EDX maps. You can see other secondary minerals, such as galena, over here. Okay, so these are really great samples to study long-term retention and migration of fission products in a reactor, because you have a complex geological history, groundwater removing fission products and actinides during the operation, you had volcanism afterwards, and really they're the only long-term nuclear waste analog that we have. Okay. So very interesting samples, and they've been studied extensively since the early 70s. Okay. And for us, these are also highly heterogeneous, and they have perturbed isotopes. So the thought was, well, this would be really where we can have a big impact. So there's a couple of other mass spectra here in the rare earth and high rare earth region. And it's really cool that by just removing the molecules, you can make a direct measurement of depleted isotopes. So I don't expect everyone to know what the normal isotopic composition is, but you can see samarium, europium-151, and these isotopes of gadolinium, which all have very large neutron capture cross-sections and are poisons in a reactor, they are depleted, significantly depleted. And in the case of gadolinium-155 and 157, they were depleted essentially to zero entirely through the reactor's operation. Okay? And all that you see here now is basically some terrestrial contamination afterwards and ingrowth from after the reactor ceased criticality and from spontaneous fission over the last 2 billion years. Okay. So here are some images that, where we're comparing, doing this interleaving between the SAMS and the SIMS. And these are on europium isotopes. Most of the europium is concentrated in the uraninite. It's outlined here. And the aluminous phosphate is very little europium. And you can take a direct isotope ratio image from these two measurements. On the SIMS, however, you see lots of false positive regions of interest. You see lots of features that aren't really there, because these are just molecules. And they change because the molecular background is changing across the sample, because it's heterogeneous. And what's a little bit perverse is that when you take the isotope ratio image, it actually looks kind of like the inverse of the true ratio image in this sample. So it'd be completely off bounds. And you can see that europium-151 is incredibly depleted based upon its isotope ratio relative to its terrestrial value of about 0.9. And a further point that should be made is that even though on a normal SIMS you can do these kinds of corrections for spot measurements, where you do this deconvolution scheme, it's really impractical on an imaging basis where you have to do it point by point. So I think this is a really valuable addition. We've looked at lots of different elements. Just show qualitatively here what happens when you have relatively refractory versus volatile elements in this uraninite grain, just an optical image. You can see that the rubidium and the strontium are relatively depleted inside of the uraninite. And one thing that was kind of interesting that we need to explore more is that zirconium, which should be compatible with the uraninite fuel, looks to be depleted in the center of this grain and enriched in the rim. So there was some migration that was going on here, and we don't really know why that is. Okay. But the main thing I want to talk about is cesium and barium. Okay. So based on the fission yield curve, this is showing the fission yields of 235, 239, and uranium-238 under different energy regimes. The majority, or the highest point, the most fission products that you get are in this cesium to barium range, kind of mass 133 to 138 or so. And these are the individual fission yields for those isotopes, and they're all about the same. And so what happens is that in fissioning, you make an isotope of a certain mass, and then it fairly rapidly beta decays into something more long-lived. And this is showing the isotopes in the part of the chart of nuclides that have half-lives longer than about 2 weeks. Okay. So you see your cesium-135, which is a half-life of 2.3 million years, 137, which is about 30 years, and then you also get a lot of cesium-133, which is stable, except that it can neutron capture and create cesium-134, which is a half-life of 2.1 years. And these all decay to barium. So why do we care about cesium? Well, it's a very mobile element. It's volatile, it's water-soluble, and it's a big problem in reactor accidents, such as at Chernobyl and Fukushima. It's released into the environment and it's easily metabolized as well. Okay. So this is a cross-section of a fuel rod, a spent nuclear fuel. So you have cladding, usually a zircaloy out here, and the fuel pellets inside. Okay. And what happens is that under all of the heat, these fuel pellets start to crack, you get fissures, and this allows for conduits for these volatile elements, such as the noble gases and cesium, to migrate to the perimeter. Okay. So if you have a rupture in your cladding or in the cask that these are being stored, these volatile elements can very easily escape into the environment. You also have small precipitates of various metals that form in here. And this is an optical image, a cross-section of that fuel rod as well. And you can really see these cracks and fissures that have formed. Okay. So cesium is incompatible with the nuclear fuel, with the UO2 structure. So it's not going to be retained in the fuel like some other elements like zirconium will be. So we decided to poke around, do some imaging on the sample, and see what we could see for cesium and barium. So these are, again, uraninite grains with a vein of aluminous phosphate in between. And you can see that the barium and cesium signals are highly concentrated in this aluminous phosphate mineral. Yeah, there's very little left in the uraninite, which is what we'd expect based on the chemistry. Okay. But when we take the direct isotope ratio images, we see this hotspot, a very large increase in overabundance of barium-135 and 137, and 138 up here that's indicative of these being fission product barium. Okay, so these were originally likely live cesium, 135 and 137, that was captured and since decayed into the stable daughter of barium in this region. Going back with EDS, we found that this is co-located with ruthenium, metal, and sulfide aggregates, which is pretty interesting. And so one of the big things is that because you have vastly different half-lives of cesium-135 and 137, and the fact that you see relatively similar overabundances of these isotopes, this tells you that, yeah, it really had to be a fairly short time scale that these ruthenium grains formed. And I mentioned for later that this particular ruthenium grain was found inside, completely enclosed within a uraninite grain, so kind of formed in situ. Whereas most of the other ruthenium grains are found on the perimeters, kind of co-located with the aluminous phosphate, such as shown up here. So these are plots of the various fissionogenic barium. So we've removed the terrestrial barium composition from these grains. Okay? So 135, 8, and 7 over here. And what we see for the majority of the grains, these are the ruthenium aggregates that were found in between uraninite grains. There's a very, very nice isochron here. So there's some sort of age correlation between these grains. And there's likely some fractionation between this one grain that we found inside of the ruthenium, or inside of the uraninite grain, that's shown in the diamond symbol. Okay? And these are all plotted relative to cesium-133. Now this is pretty tricky because unfortunately cesium, stable cesium, is monoisotopic, so you can't go through your normal method of subtracting away the cesium contribution because you don't know whether the cesium is all fissionogenic or some was added later. So that's a bit tricky. But keep in mind that that ruthenium inclusion is very different from the others that were found in between the uraninite. Okay. So we can reconstruct and reparameterize this isochron. And I apologize for the strange formatting that's here. But basically, when you plot fissionogenic barium-135 versus 138 against 137 versus 138, all of these grains are collinear on line. So they definitely all share an age relationship. And we've removed this dependence on cesium-133, which is a bit fickle. And we can take the slope and the intercept of this line and find that for both of these instances, we estimate about 4 years versus almost 6 years for an average of about 5. So these ruthenium aggregates formed, we presume, after criticality ceased, just 5 years, within 5 years, and captured live radiocesium within them. So this is pretty incredible, and it was something we were not expecting to see. You can plot the other isochrons we parameterized. Again, this is the one that you saw previously, others versus cesium-133. But all of these slopes and intercepts are a bit nonsensical. So it's difficult to make sense of this, just because we don't know what happened to the cesium. What's interesting in these ones is that they are still collinear in this fashion. We can also look at barium-134, and all of the grains that are in between the uraninite are collinear, but the slope and intercept are also nonsensical, so we're not quite sure what's going on here. But there's some fractionation that's happening, where you have to have cesium-133 in order to neutron capture to cesium-134 and decay over here. So it seems like with no cesium-134 in the included uraninite grain, there was clearly fairly efficient flushing of this cesium out of the uraninite. There wasn't enough 133 around to neutron capture and make the 134. Okay, so now we have to, because this is a relative age dating technique, we have to figure out what is the anchor for this. It could be basically three situations. You could have formed this at the start of criticality, you could have formed it at the after criticality or at the end, or somewhere in the middle. And so these are the lines of evidence that we believe point towards it forming after the reactor finally ceased. The first of which is that cesium is fairly efficiently washed away from the uraninite, so you're not retaining much. So while the reactor is cycling on and off, you're not keeping the cesium around in the uraninite fuel very long. Okay. Also, most of these ruthenium grains that we found are quite large. They're anywhere from 25 to 150 microns in size. And all of the ruthenium, because it's an incredibly rare element, the second rarest on Earth, all that ruthenium is fissionogenic. So you had to have enough time for the reactor to be operating to build up enough ruthenium inside of the reactor to actually form these relatively large grains. In anthropogenic reactors, epsilon particles are what these ruthenium and other metal aggregates are called, and they're usually far smaller on the micron or submicron scale. Okay, so this points towards it being towards the end of the reactor operation. But they also share an age relationship. And this is important because I would expect, naively, that if these formed at different times during the reactor's operation, they would probably all have a different age relationship. They'd be scattered on that isochron, okay, because they can capture different relative amounts of the 137 and 135. Because certainly you can build up a larger concentration of 135 because it has much longer half-life. So this points to these grains forming 5 years after the end of criticality in this site. And we look back at these plots again and try to look at the fractionation. Okay? So you see a lot more barium-138 in the included grain relative to the excluded ones, and also slightly higher amounts of cesium-137 and 135 in here, but no 134. So because the amount of barium-137 is so much more than the amount of 135 and 137 in this grain, and they're all produced at roughly the same proportion from fission, we can deduce that at least the cesium to barium fractionation is in the realm of about 1.2 to 2.4. So cesium is lost from the uraninite at least this amount faster or more easily than barium. Now, it'd be great if we found other secondary minerals like these that we could use to try to nail down this fractionation. And unfortunately, all we have is what's lost from the uraninite, which we can't really measure except indirectly, and we have all of these ruthenium aggregates. But we don't know exactly how ruthenium fractionates cesium and barium either. But luckily for us, most of these were captured while the radiocesium was live. Okay. So what is the application to fuel storage? Now, cesium-137 is one of the major health risks, as I mentioned before, for nuclear reactor accidents and medium to short range storage of the fuel. Okay, because it's highly soluble, highly mobile, soluble in water, and it's distributed uniformly in the body. So it's somewhat difficult to get rid of. So for long-term storage, usually what happens is you try to vitrify, you make a glass, and you pour in some of the fission products and the fuel. And we know now that ruthenium can capture the cesium, although ruthenium is very rare. One bonus is that you produce a lot of it, several percent of ruthenium in the fuel itself, so you wouldn't have to necessarily add this to the vitrification process afterwards to try to stabilize everything. But of course, the chemistry for nuclear fuel storage and reprocessing is incredibly complex because all of the elements behave differently. You create this whole soup during the fission process, and particularly actinides, which make up most of the fuel waste, and the fission products require different chemistries and behave differently. But it leads to the interesting question, can we now design better materials that can capture the cesium either in the short-term cask storage or at a nuclear power plant in case there is a meltdown or an accident. We know that some of these volatile elements can be captured. So what can we do? So we got a bit of press for this work that came out last month, which is kind of exciting. First time for me as an author to be picked up by mainstream media. So just a few of the articles that came out. Also had a radio interview on Science Friday. I don't know if any of you heard, but I wish it could have gone a little better. I have to say that during the interview, someone was doing a sound check in my headset while I was interviewing, saying, "Say Peter Piper picked a peck of pickled peppers," which is very distracting, inside of your head. So I wish I could have that one over. Can you hear me? All these things run through your head. It's like, is this normal for radio? I've never done radio before. It's not, but okay. So even if you're not a proponent of nuclear power for the future, for whatever reason, the fact is that we have 250,000 metric tons of commercial nuclear waste that's currently in temporary or pool storage, all temporary. This isn't long-term storage because there isn't a good long-term repository at the moment. You have naval reactors being decommissioned, such as the Enterprise, lots of medical waste. Cesium-137 is useful for medicine. And, of course, thousands of stockpiled nuclear weapons that will eventually need to be decommissioned and stored. Okay? And for those of us who are interested in space exploration, we should want that some nuclear program should exist because we like plutonium-238 as a radioisotope power system for Curiosity or the Voyager probes or anything that wants to go underwater on a planet. Okay. So some of the ongoing work that we're doing, and I'll try to wrap up, we're doing FIB-TEM of these ruthenium aggregates. We've cut out a section already. And we'd really like to know if we can differentiate between the metal, oxide, and sulfide phases. Which one, do they differentiate, or sorry, do they differentially capture cesium or barium? So hopefully we have the sensitivity to be able to see this in situ, and if not, or in addition, maybe we can do some nanosims on it afterwards, because that'll enable better design of materials in the future. And we have some collaborators sending some more Oklo samples. There's one other zone that has these ruthenium aggregates, although they're qualitatively a bit different than zone 13. So it'll be pretty interesting to see if the other reactor zones operate in a similar fashion. We can see. So just to wrap up, the Oklo samples have been exhaustively studied since 1972. And it's kind of a waning interest in some of these samples. But the application of new technology yielded immediate results. So we should continue looking at these, continue developing new technology. And of course, this is the fact with any technology that comes out. The nanosims revolutionized the cosmochemistry field. So we should keep pushing forward. And Nautilus is pretty great. I'm having a good time with it. So we have some other projects going on in cosmochemistry. Of course, always looking for collaborators, nuclear forensics, and the pre-solar grains, which is my background in meteoritics. So anyway, just acknowledge some of the collaborators and the people who work on the projects, and thanks.
Evan? Questions? Great.
Chemical attraction of cesium and barium.
It does. So barium is known to make a stable compound with ruthenium. It's like barium, ruthenium, O4, perhaps. But cesium is surprising. I agree. So we definitely need to do more work.
But this has to be diffusion to grow these, making ruthenium an atom at a time by the fission.
Right.
And then you're diffusing it.
Exactly. So I don't know if I can go back really quickly, but based on those EDX maps, you can see that I broke it. Oh, here we are. Okay, so sorry if the colors are difficult, but the ruthenium is mostly uniformly distributed throughout the uraninite, but there are a couple of these larger grains that form. And some of it clearly migrates out as well.
So I might have misunderstood this a little bit, but you're arguing that the cesium is in these little grains are after criticality, after the last years of this reactor going on, then they're being preserved.
Yes.
Right? So where's the rest of the cesium going from that 10,000 years beforehand, and what proportion of that is included in? I mean, is this just the last step, or is this some aggregate from the last 5 years of cesium production?
Right. It's more of the latter. We know that the fission products, especially cesium, were washed away by the groundwater that was continuously coursing through. The trick with cesium-133 that's there is we know that there's a high abundance of it in here, but we don't know, was that from the reactor? Was it from later processing during the last 2 billion years? We don't really know. But based on the evidence, it does seem like we can put that stopwatch after criticality. But it's a tricky problem. And just to mention, the other reactors that were going on during this time, they're far-flung geologically, so they're not going to influence this with heat or anything else.
What's the size of
Yeah, so in order to have a natural nuclear reactor like this, you need at least about 1 meter cubed of material, just because that's the neutron mean-free path that. I mean, they're all about that size. Yeah, that's a good question. So people have been searching for uranium deposits for a long time and have done it fairly extensively. This reactor, so there may have been other reactors in the past, but one nice thing about this is that it was made in a sedimentary basin, and it wasn't metamorphosed or changed in the 2 billion years afterwards, where most of the other uranium deposits are, in igneous or metamorphic regions, and they just have been, potentially obliterated. So that's one thing. The other is that it's actually this was like the exact time that you could have a natural nuclear reactor occur. It couldn't have happened too much earlier because you couldn't make these UO2 deposits because there wasn't enough oxygen, and it couldn't have been too much later because the uranium-235 was too low in abundance. So it just happens to be, that improbable. It happened then.
Okay, well then let's thank Evan again.